This is problem 1513. It's on page 665. The belt shown moves without slipping over two idler pulleys. At the instant shown, the velocity of point C is 400 millimeters per second to the left, and its acceleration is 600 millimeters per second squared to the right. Determine A, the angular velocity and angular acceleration of each pulley, and B, the total acceleration of point A, C, the total acceleration of point B. That's a lot of points. Let's draw them. Figure out what's going on here. Point A is up here at the top of the wheel. And the radius here is 0.08 meters. Point C is between, and then point B is there. And the radius is 0.05. Now the belt continues down here, but I'm going over my radius line. Do you understand what they're asking? That they're telling us that the velocity of C is 0.4 meters per second. So I did that right. 1, 2, 3, yeah. But the acceleration of C is 0.6 meters per second squared to the right. Now, we understand the acceleration of point C. It's just a linear acceleration. But how about point A and point B? Why would point A and point B have any other acceleration than this 600 or 0.6 meters per second squared? Why would there be any difference?
The radius of the pulleys.
Okay, what about the radius of the pulleys?
It would be slower.
They're going to have higher or lower acceleration than C? Here's the key. This is the linear acceleration of point C. Since the belt will not stretch or shrink, the tangential acceleration, because notice point B is moving about a curve at this point in time. So is A. The tangential acceleration of A and B is exactly the same as the acceleration of C, but since both B and A are moving around a curve, they will both have a normal acceleration. Now, A is going to maintain the normal acceleration for quite a while because it's going to move around here. B is going to lose its normal acceleration in the very next moment. Do you see? Because B is about to start going straight rather than going around a curve. Okay? So, I'm assuming that they're talking about this point just before it arrives at B. If we're literally at B and past the curvature, then B has the exact same acceleration as C. There's no difference. But I don't think that was their intention. I think their intention was that B is still moving on a circular path. Now, how do we quantify this normal acceleration? What do we do with that? Well, there's a couple different ways of dealing with it. Remember when we dealt with normal acceleration way back in chapter 11? What was the equation for normal acceleration? Do you recall? It was a tangential velocity squared divided by the radius. That's right. Once we got to chapter 15 that we're in right now, we found that you could also write this as omega squared r. Right? Because V is omega r, so when you square it, one of the r's cancel, but the omegas don't. There's still two omegas there. So we can relate the normal acceleration of B and the normal acceleration of A to the angular speeds of those two wheels. Right here. Okay. So why don't we do that? Let's calculate for B the normal acceleration. We need the angular speed of B. We don't have that yet, but we can get it. In fact, maybe it wouldn't be the best to get the angular speed of B. Maybe it'd be best just to use this equation. So that's what we'll do. The tangential velocity of B will be exactly the same as the tangential velocity of C. So that's going to be 0.4 meters per second, quantity squared, divided by the radius at B, 0.05 meters. Now, when you plug all that into your calculator, you should find the normal acceleration of B. Now, I did that here somewhere. Yeah, here we go. I came out with 3.2 meters per second squared. If you do the same thing for A, the normal acceleration is 0.4 meters per second, quantity squared, divided by, because notice the linear speed at A is the same as C and B, divided by, though, the radius of the other wheel, 0.08 meters. When you plug all that in, you should find a normal acceleration of 2 meters per second squared for A. Okay, so there's the normal acceleration for point A and point B. If we want the total acceleration, then we have to, we have to perform a vector sum of the normal and tangential accelerations. Okay. Now, I didn't do that. What I did is I simply wrote the acceleration of A as a vector, because the acceleration of A is going to have a component in the tangential and in the normal direction. So I just set up a coordinate system, x, y, like this. That way I could write down the acceleration of A in the x direction is simply the same as the acceleration of C. Okay, that's just the first piece, that's just this piece, this tangential piece. But then I can add to it the normal acceleration. Now notice the normal acceleration goes against the coordinate I chose, so it's going to be a negative thing. The magnitude I've already calculated right there, 2, is in the j direction. Both have units of meters per second squared. For B, we can do the same thing. For B, its tangential acceleration will be exactly 0.6 meters per second squared. Just like C and just like A. Like I said, the tangential acceleration, ABC, is exactly the same. C only has tangential acceleration.
Are they in the same direction too?
I'm sorry?
The tangential acceleration for A
Right, there's a tangential acceleration for A.
in that direction or the other one?
It has to be in this direction, because if C is accelerating in this direction, then A and B also have to accelerate in that direction. If not, then their linear speeds will be different and the belt will break or it will shrink.
Okay.
Good question. Any more questions? These are good. All right. So, you guys help me out. What's the last thing I need to put in here for B?
Negative 3.2.
Good, 3.2. Good. So there are the accelerations of A and B. Now, I should have calculated the magnitude. In fact, I did. Just noticed on my sheet. So the magnitude of the acceleration of A, you just take the square root of the sum of the squares, right? So 0.6 squared plus 2 squared square root. When you do that, you get 2.088 meters per second squared. When you take the magnitude of the acceleration of B, you get 0.6 squared plus 3.2 squared square root. You get about 3.256 meters per second squared. So why is it that even though the motion of A, B, and C are very closely related, why is it that B has the biggest acceleration of them all?
Because it's the smallest field.
Smallest wheel, right? It's changing its speed quicker than the rest, because not only is it changing its speed in the horizontal direction, it's changing its speed in the vertical direction. And since the curve is the tightest there, it's changing its speed the fastest. Okay. So this takes into account both the direction and the magnitude change. Questions, comments? All right.